Okay, it's Math 151. It's time to start. Next Tuesday, what's going on? We have the second exam. Tuesday night, March 5th, 7:05 to 8 o'clock. You should get there early. Not for me. I don't care if you come early. All right? But I think you should care if you come early, because you want to be sitting down, you want to be comfortable, you want to have a seat that you like, and then we can pass out the exam and you can start on time. That's what you want to do. All right. Oh, and it's the same place it was before. CM, what the heck's CM 200? Oh, Campbell 200. And there's an upstairs and there's a downstairs, right? I'll be sending you an email. It'll be similar to the email I sent last time as to where you should sit, upstairs or downstairs. Try to follow that. Because, see, the upstairs can only hold 100 people, and the downstairs can only hold 150 people or something like this, and we have 220 people. So if everybody goes upstairs, it's a problem. If everybody goes downstairs, so we have to kind of, you understand? All right. I'll be sending out an email reminding you when and where the exam is, too. How do you study for the exam? You got to work problems, and there's problems on Carmen. There really are. If you can't find them, one of the TAs was talking to me. He didn't know where they were. He's a TA. Of course, he doesn't really care. He's just going to Carmen for kicks, right? You guys should go there. It should say exam. Has anybody seen this? Somebody has seen this from our class, so it's been confirmed. And there's other exams you can work with, word problems and all kinds of stuff. Here's something I'll tell you about exam 2. This is not a secret. What I'm about to say is not a secret. You have to be an expert at taking derivatives. Every single question, pretty much, is going to ask you to take a derivative. Taking the derivative is not the hard part of the question. That's the part that you cannot miss. All right, so if you have to practice derivatives until you are an expert, until you say, I dare you to throw me a derivative question just asking me to take the derivative, because that I will 100% get right. Does that make sense? There can be no, if you go in there and there's any doubt in your mind that you can take any derivative that I throw at you, you're in trouble. Start studying now. You have to be an expert. And if you can take all the derivatives in the book just fine, that does not mean that you're going to get 100 on the exam. That just means it's not going to be a total. It's going to be tough, right? You have to be an expert at derivatives. I'm not kidding. If you're not, it's going to be a disaster. So what are you going to do? We're going to go home and cry? That's what I'm going to do. That's what I do every night. But you guys are going to go home and you're going to put on, Eye of the Tiger, and then start doing derivatives. All right, I think that's all I have to say for now. Today, we're doing chapter 4.1. It's the last chapter that will be covered on the exam. And to be honest with you, every time I look at the material in 4.1, I'm always like, how am I supposed to teach this? But I'll figure something out. Okay, it's not that hard. It's not that hard. Let me make sure by the way, has anybody noticed that the videos are totally up to date? I've gotten better. They're totally up to date. Does anybody else know this? If you go to Carmen, click on content, or I even have a playlist now. I got a spam email asking me if I wanted to make my videos go viral. Oh yeah. No more cat food for Bart. So now, Math 4.1. So we need some vocab. We need some vocab for this section. First piece of vocab, extremum. This is just a max or min. Maybe I'm doing this vocab in the wrong order. That's okay. Of a plot. That's what an extremum is. It's just I think the maximum is the highest point. The minimum is the lowest point. So extremum. That's the first thing. Now, yeah, I feel kind of bad. But, so max, if we just say maximum, this could be, this means this is the absolute. This is typically how about this? I'm going to change. I'm sorry, guys. I'm erasing. It's a high point or low point of a plot. It's a high point or a low point of a plot. A maximum is the absolute highest point. It's sometimes called an absolute maximum when they really want to emphasize it's the biggest point. Sometimes. But if they just say maximum, they always mean absolute maximum. It's the maximum, just like we're at the, yes? Yeah, absolutely. That's the next definition. Local max. This just means you're greater than all the points nearby. So x equals a is a local max if f of a is greater than f of b for all b near a. That's the local max. And a min is the absolute minimum, absolute lowest point. And a local min, that's the same thing as local max, but with the min put everywhere. So x equals a is a local min if f of a is less than f of b for all b near a. And here I say high point or low point of a plot. And this could be like, this could also be local. These could also be locally high points. So if I say extremum, you say find all extremum. Well, so here are the local maxes, here are the local mins, here are the absolute maxes, here are the absolute mins. But really what's going on here is we should have a picture. We should have a picture. So I will draw an easy picture here. So if here I have, I don't know, this could be -2, and this could be 7. And I could have some curve. There's some curve. Whatever. There's f of x. So here I have my min, and here I have my max. And I want to see something real quick. Okay, it looks like one of the questions that often comes up here is whether or not is x equals a the local max or is f of a the local max. You understand the question? It looks like in our textbook we're saying that let's say, I'm really sorry here, gives a local max. And we'll say gives, okay, and the local max. So f of a is the max. F of a is the min. And so here is the value of the min, and here's x equals, what could this be? X equals minus 1.7, and this could be x equals 6.7 right there. And this is f of 6.7. That is the max. So, how does anybody know why this topic, let me ask you this, okay, let me rewind. How do you know when you're doing a calculus problem? I give you a math problem, and you say, aha, this is a problem from calculus. What features make it a calculus problem? What? He says, I'm guessing you're taking a derivative someplace. That's a good guess. If you're taking a derivative, derivatives are calculus problems. Often have derivatives in them. How is this idea of extremums, maxes, mins, local maxes, local mins, how's that related to derivatives? A point on a function. Measuring change. So derivatives, one of the reasons that calculus is hard is that derivatives do lots of things. They measure change. They are a limit, right? They are. Do you remember that from the first exam? Compute using the limit definition of derivative, right? They are a limit. And they are a set of rules. We've learned a bunch of rules, right? Rules. What else is a derivative? Yeah? Yeah. I have. You know what I did here? I wanted to write the min, and I wrote the min. There we go. I just write th and then put an m after it. That's crazy. What else are derivatives? So the measure of change, they are a limit. They are a set of rules that you do. What else are derivatives? What else are they? Someone says, what's a derivative? It's a function. It's a function that gives the slope of the tangent line. Can you guys see this with this thing here? This thing's going to be moved. It's a function that gives the slope of the tangent line. It's a function that gives the slope of the tangent line. All right, so that's 4 things that the derivative is. This is one of the reasons that calculus is hard, because in real life, things are typically only one thing. A derivative is already 4 things in our class, and it's going to become 5 before today's over. So, and to be able to do a calculus problem, you have to be able to fluently go between these different ideas. You have to say, well, it's a bunch of rules. I know all the rules. You have to say, I know the concept too. It's a function that gives the slope of the tangent line. You got to say, well, it's a limit. Well, sometimes that's important. Measure change. To be able to do it in our word problems, that's why we're taking the derivative, because we're trying to find the rate of change. All right, so how are we going to use it to help us with maxes and mins? Some people know this answer. I know you do. It's where the derivatives, he says the derivative is 0. And what's 0? Here's something else a derivative is, which I'm writing in blue for some reason. It's something you set to 0. Something you set to 0. Something you set to 0. He says, at the local maxes and mins, what's the slope of the tangent line? Yeah, the tangent line's horizontal at the maxes and the mins. Here's the max. Here's the min. The tangent line's horizontal. This has 0 slope. Or a better way to say it, slope of 0. And so here's an idea. It's something you set to 0. So these have slopes of 0. Is it always the case if you have a max or a min, then the slope of the tangent line will be 0 there? Is that always true? Maybe it doesn't. Somebody said it couldn't exist. Who said that? Maybe it doesn't exist. Can you give me an example of a function where the derivative does not exist? A cusp or a corner? Good enough. I buy it. He says maybe the derivative does not exist. And here is a function where the derivative does not exist. Well, I'm trying to draw it. This is supposed to be the absolute value of x. And where's the minimum of the absolute value of x? 0. And what's the derivative at 0? It doesn't exist because from the right, it's 1. And from the left, it's -1. When you take the limits from the left and the right, the limit doesn't exist, right? So here's the conclusion that I'm very slowly trying to make, if I can find the eraser. I think I can. Okay. Oh, here it is. The conclusion I'm trying to make is, if we're interested if we are interested in finding maxes and mins, then we should check where the derivative is 0, should investigate where the derivative is 0, and where it does not exist. X values where this happens. Where f prime of x is equal to 0, or f prime of x does not exist. They're called critical points. Those are called critical points. So if I give you a function, the first thing you want to do is you want to find, and you want to know its maxes and mins, the first thing you want to do is find its critical points. So let's do an example. So f of x is equal to x minus 2x cubed. What are the critical points of this? What do we have to do? Take the derivative. So f prime of x is equal to 1 minus 6x squared. Thank you. And so if we set this equal to 0, 0 is equal to 1 minus 6x squared. -1 is equal to minus 6x squared. 1/6 is equal to x squared. Square root of 1/6 plus or minus is equal to x. What do you guys think? Are those critical points? All right, great. Those are critical points. Does this curve necessarily have a max or min at the critical points? I found a critical point. Does this mean there are maxes or mins here? He says no. Can you give me an example of a function whose derivative is 0 or so these are the critical points. I'll write that down. Or just, can you tell me how to draw a picture of a plot of a function where the derivative is 0, but we don't have a max or a min? Yeah, and so this guy just drew for me a picture in the air, like you would with a sparkler, right? Next 4th of July, when you get your sparklers out, you should do your favorite calculus functions, okay? It's lots of fun. He drew this function for me. This is f of x is equal to x cubed. And we have a critical point here. We have a critical point right here. What's the slope of the tangent line here? It's 0. Is that a max or a min on the entire real line? No. Not a max or a min. So, the first step is to find the critical points, because that usually when you take the derivative of a polynomial, what happens to its degree? It goes down. That means it's easier to deal with. Higher degree polynomials can be almost impossible to deal with. When I say almost impossible, I mean impossible to deal with. When they're lower degree, this cubic, much harder to deal with than the quadratic, we can do something with it. And then what you can do is you can check the critical points. And the most naive, and I don't mean naive in a bad way here, I mean it in a good way. Like, I don't need to know anything. I'm naive, and I'm still going to be fine on this test. Okay? That's who I am. I'm going to plug this point in, and then I could just plug in points nearby, right? And say, is this a maximum or is this a minimum? That's one solid strategy. I found the critical points. If I have a maximum, then it has to be at a critical point. And then I check, right? All right. There's one more. Boy, I'm not sure if this will help, but I'm going to say, so if we have maximums, if we have, now there's a little, now forget this, don't write this down. I'm going to give you the next theorem. The next important thing to know is life is a little different if you're working on what's a closed interval? What's that mean, closed interval? Does anybody know what, yeah? It's between 2 points, a closed interval. Closed intervals have their own little business. They're like their own thing. You're between 2 points, between and including two points. So if you say pick a number between 1 and 10, the next question you might want to ask, am I allowed to pick 1 and 10, right? You're really asking, are you on a closed interval? And when they say yes, you say, okay, pi. And they say, that's not what I was thinking of. But anyway, so between 2 points. And remember, you do it like this. You write A, B. And this means A less than or equal to X less than or equal to B. These are closed intervals. When you're on a closed interval, the rules are a little different. Because check this out. Let me draw a picture and then show you what I mean. We already said x cubed. Does it have a critical point at x equals 0? Does x cubed have a critical point at x equals 0? What's the derivative of x cubed? 3x squared. Plug in 0. You get out 0. So x cubed has a critical point. Does x cubed have a max at? No, not typically, if you're working on the interval r. However, well, this is not a very good picture of x cubed. There we go, that's better. It's more flat. However, if I'm working on the closed interval, you typically use dots like this, closed interval, right? Closed interval, 0, 1. consider f of x equals x cubed on 0, 1. Find all maxes and mins. Find maxes and mins. Well, where's a max on this interval? At 1. We're only going from 0 to 1, right? We're only going from purple. Purple is outside. Purple is outside. Purple is a wall that we stop at. This is 0, that's 1. What's x cubed at 1? So we have a max at 1, 1. And where's the min at? 0, 0. When you're working on a closed interval, you can have maxes and mins where you maybe wouldn't usually have them. And I'm going to state exactly what I mean by this. I'm going to say, so here it is. This is called the extreme value theorem. The extreme value theorem if f of x is continuous on a closed interval AB, then its maxes and mins are either at its critical points or its endpoints. Well, I'll say max min is at the critical points and or the endpoints. And so in this case, the maxes and mins, the max min, the minimum was at the endpoint, right? And the maximum was at the endpoint. The extreme value theorem, if you think about it for just a second. This should be like, if I think, and I hope this is, I really think that this, you should be like, yeah, of course. Yeah, extreme value theorem, yeah. Yeah, I draw a picture. The idea is you have to go, you have some closed interval, and so it's closed, so you count the endpoints. Here they are. Here's the endpoints. They're in bright green. Here they are. These count. And then I'm going to try to draw. If I try to draw a function that doesn't have a min or max, see, the minimum's here at the endpoint, right? It should make sense. This is a very sensible idea. What if I change the closed interval to an open interval? Remember open interval? What about open intervals? We shouldn't worry about this too much, but we'll say something. What about open intervals? So what's an open interval again? Yeah? You don't have the endpoint. So you write this a, b, and this is a, strictly less than x, strictly less than b. And so let's do this same example. Let's do x cubed, but now we're going to do it on this open interval. And so there's x cubed, and I'm going to draw, I don't want to get chalk all over my, okay, so now this is open. This is open, right? So we don't count the endpoints. Do we have a minimum in this interval? He says no. He shook his head no. Now, of course, I kind of asked, can you tell me why? I know I'm putting you on the spot. I'm sorry. No? That's just a hunch. That's good enough. Can anybody tell me why we don't have a minimum when we have open intervals here? Yeah? Yeah, and what were you going to say? Both answers are very similar. There's an infinite number of numbers going to 0. You can get as close as you want to 0. The minimum's at 0, but is 0 inside the interval? No. So to use this extreme value theorem, you have to be on a closed interval. Also, you have to be continuous. You have to be continuous. So let's see if we're not continuous, what happens then? My mind has gone blank. If you're not continuous, what are you going to look like? I could draw something like this. No, I'm not thinking right now. Let's do some examples. Sound good? Is this pretty easy or is this hard? It's very hard, Bart, but if we study hard enough, I'm sure that we can learn how to do this. I think this is much easier than the related rates problems. All right. Let's find the local maxes and local mins of a couple things. Find local maxes and local mins. All right, so that just means where you're slightly above, slightly below something. Let's see. Let's do this one. Y equals x squared minus 1 over x. What are we going to do here? Take the derivative. So we write dy over dx. And that's equal to, oh my God, how do we got to take the derivative here? I'll do it like this. X squared minus 1 times x to the minus 1. How's that look? And now I'm going to use the product rule and the power rule and the chain rule. So doing the product rule, I'll take the derivative of this piece first, and I will get 2x minus 1. Is that correct? Oh, no. I get 2x. Is that correct? And then I multiply by x to the minus 1. And now I add. Now this piece stays the same. And I get x squared minus 1. And now I take the derivative of this piece here. And so it's going to be minus 1 x to the minus 2. Is that correct? I was wrong about the chain rule. We don't have to do it. I'm sorry. So here's my derivative. Oh my God, this looks terrible. Not so bad. What we can do is what's 2x times x to the minus 1? This is just 2. And now we can 2 plus, and this is x squared minus 1 all over, well, let's do, it's actually minus, this is that minus right here, x squared minus 1 all over x squared. Is that right? Somebody's looking at this with a scowl on their face. Yeah, sorry.
Why don't you distribute the x to the negative 2 to get rid of the x squared?
Yeah, I can do that. I mean, I can do it at this step right now, actually. So she says, hey, distribute the x in minus 2. That's the same thing as splitting this up into two fractions and canceling right here. So this is going to be 2 minus 1 plus 1 over x squared equals 1 plus 1 over x squared. All right, so there we are. So we want to find local maxes and local mins here. What do we do now? We try to find out where the derivative is equal to 0 or where it does not exist. Where does the derivative not exist? Yeah, x equals 0. So we have critical points. First of all, when does dy over dx equal 0? Can you guys just tell me the answer to this? When x is equal to this guy's shaking his head no, and I'm interpreting that. We would like to think when this is right, it's x squared, so if you plug in -1, this thing's never going to go away. So never, never. That's not a good way to say this. Never. So when does dy over dx not exist? At x equals 0. So now the question is x equal to 0, is that a local max, a local min, or neither? And what's the most naive way to do this? Plug in points, right? Look, this thing has to have, if it's going to have maxes or mins, it's going to have them only at these critical points. So now we plug in points close to 0, and I have a calculator here. Now, hope I don't need it. We'll find out. What point should I plug in? 1. 1 sounds fantastic. 1 squared minus 1 is 0. Divided by 1 is 0. Okay, so at 1, f of, or I can say f of 1 is equal to 0. And then f of -1 is equal to f of -1 is equal to, that's not very helpful. What's going on here? Maybe we should try a different point. Give me another point. 0.1. Okay, so let's go closer to 0, he says. So now f of 0.1 is 0.1 squared minus 1 divided by 0.1, right? 0.1 squared. What's that going to be equal to? Oh, geez, I'm looking at the derivative. I'm sorry. It's 0.1 squared minus 1 all over 0.1. Wait, did I do this wrong? Is this right? This is right, right? Yeah. 0.1 squared minus 1 divided by 0.1. What is that? Is it positive or negative? It should be, let's see, negative, because 0.1 squared is very small, minus 1, so this is negative. And how about put in negative 0.1 squared minus 1 over minus 0.1. Is that going to be positive or negative? Positive. And can I evaluate this thing at 0 here? No, so what's going to happen here? What do you think this is? A local max, a local min, or neither? It's probably neither. Neither. It's a tough problem. Let's do a different one. All right. How about local maxes and local mins of f of x equals 2 plus 3x minus x cubed? What do we do first? Take the derivative. F prime of x is equal to 3 minus 3x squared, right? Set this equal to 0. Did I do that right? Okay. Set this equal to 0. 0 equals 3 minus 3x squared. So minus 3 equals minus 3x squared. 1 is equal to x squared. X is equal to plus or minus 1. These are the critical points. Are the critical points where we have maxes and mins? Maybe, right? They are where the derivative is equal to 0 or where the derivative is undefined. Critical points are where the derivative is equal to 0 or where it's undefined. We may or may not have maxes or mins there. Okay, so x equals plus or minus 1. So we want to know, are either of these maxes or mins? We should try to plug in values here and see what happens. What is f of 1? F of 1 is equal to 4. F of minus 1 is equal to 5. 2 times negative 3, 2 plus negative 3 minus 1 is negative 1 minus negative 1. So 0. 0. Okay, and now we could start to sketch a plot if we wanted to. And so 1 is 4, negative 1 is 0. And now what should we check? Points in between, right? What's f of 0? F of 0 is 2. So 0 is 2. What's f of negative 2? So this is x equals negative 1. This is x equals 4. This is 0. I want to know x equals negative 2. Where's x equals negative 2 here? What's that going to be? Let's see. That's going to be 2 plus 3 times negative 2. 3 times negative 2 is negative 6. 2 plus negative 6 is negative 4, right? And then negative 2 cubed is negative 8. So negative 4 minus negative 8 is negative 4 minus 2 cubed minus 4 minus negative 8, negative 4 plus 8 is 4. Okay. How about x equals 5? X equals 5. What's that going to be? That's going to be 2 plus 3 times 5 minus 5 cubed. Is it positive or negative? It's down here someplace. What's our curve look like? Right? So x equals negative 1, it's a local min. X equals 4 is a local max. All right, that's not so bad. Let's do another example. Okay, how about this one? Is that the same one we just did? No. How about sine squared of x on pi over 4, 5 pi over 3? Closed interval. So what do we use to do this? We got to use the extreme value theorem here. Well, that's what we should use. So we take the derivative, right? What's the derivative of sine squared x? It's going to be sine. It's going to be 2 times sine of x times cosine of x. Chain rule, right? It's the ghost of Knowlton Hall, okay? All right. We could all just sing back. So now, we want to know when the derivative equals 0. All right, so on this interval, pi over 4 to 5 pi over 3, when is this thing equal to 0? Oh, does this seem hard? Is this hard or not? She says yes. Okay, good. Good. Okay, this thing is only 0. It's only 0. This is all multiplication, right? So this is only 0 if one of these is 0. That's only 0 if one of those is 0. And sine, and you really, we need to know, we must know everything about sine and cosine. Really, I don't know anything about sine and cosine, to be honest with you. So I guess you got to know something about sine and cosine. There's one of them. Here's the other one. Which one's which? Awesome. Sine's on top. And so I know this one's sine of x, and this one's cosine of x. And sine of 0 is 0, right? Of course, 0 is not inside our interval. Shoot. Okay, so now, what's this piece here? Where's cosine 0? Cosine is 0 at pi over 4. Remember, we plug angles into cosine and sine typically. So pi over 4. So this is pi over 4. We're going up like this on the unit circle, right? And so the cosine is 0. And now let's see. When's the next place? When's sine going to be 0 here? At pi, going around the unit circle. I have no idea. This is pi over 2. That's pi over 2. Now everybody's happy. So we have pi over 2. It's 2 pi over 4, right? Pi. And then where's the next place that one of these things is 0? Three pi over 2, right? 3 pi over 2. Okay, so is 3 pi over 2 less than or greater than 5 pi over 3? Here, 3 pi over 2, is 3 over 2, how is it related to 5 over 3? What is 3 over 2? Put it into decimals for me. So 1.5. What's 5 over 3 equal to? What's 3 over 3 equal to? What's 1/3 equal to in decimals? 0.3 repeating. So this is 1 plus 2/3. So this is equal to 1.6 repeating. Okay, so 3 pi over 2 is in here, which means that we can start to write down all the critical points here when the derivative is 0. The critical points are exactly at critical points are at x equals pi over 2, because that makes this thing equal to 0. X equal to pi, that makes this one 0, right? And at x equal to what? 3 pi over 2, right? Does the derivative exist everywhere? Yeah, it exists everywhere. There's no division by 0. There's no any of that. That's how they don't. So now what you do is you just evaluate the function at all these points. What is sine squared at pi? What's sine of pi? 0. Sine of pi is 0. Sine of pi, ooh, there it is, 0. Squared, so here the function f of x equals 0. F of pi equals 0. F of what is sine of pi over 2? 1. So this is f of pi over 2 is equal to 1. And now we have f of 3 pi over 2, which is equal to 1 as well. And now you need to compare with, this is f of x, by the way, f of the endpoints. You just check the endpoints. So pi over 4 and f of 5 pi over 3. And you see what these equal. And you can either do it thinking about it. What is sine of pi over 4? Radical 2 over 2. And what's radical 2 over 2 squared? It's going to be 2 over 4, which is 1/2. Okay, does this look like one of the maxes or mins? No, this one's a little harder. What's 5 pi over 3? I'm not sure. Does anybody know 5 pi over 3? What'd you say to me? I'm just hearing, all right, so your homework from me is to evaluate this 5 pi, and so see if it's bigger than or less than one of these values. And that's going to tell you maxes or mins. We're done.